sums and differences of polynomials today, shall we? And in order to introduce this idea, let's say a few words about what we call powers. All right, and this is, I think, quite a familiar notion to you. If we were to have, say, a to the 1 power, you and I simply write this as a, and of course a squared, if I were to use the symbol a with a little 2 up there, we all know that means a times a. If we were to write, say, a to the 3rd power, or else a cubed, we know this is a times a times a. Notice here we have 3 factors. And if we were to continue this and write a to the nth power, how then may we write this? But, well, let's use some symbolism. A times a times, and let me put in some dots here to indicate that we have some factors missing, and finally have some factor of a there. And how many of these factors do we have? We have n of them, is that right? We have n factors, all right? And we call this number a here, it's given a special name. We refer to that, Glenn, as the base of our power, and we then speak of this number n up there as the exponent. That's called the exponent, and the whole thing then is simply referred to as a power, okay? And from this notion of power, it's then quite easy for us to look at what we call a monomial. And a monomial, for example, suppose we were to write something such as 12x cubed, all right? In which here we have a numerical coefficient, or simply a coefficient, and some base, and then some exponent here, or else negative 3x to the 5th power, 17 x to the 4th power, and so on, are all examples of monomials, is that right? And let me use the notation of a times x to the nth power, where this number a here now is thought of as what? This we call down our coefficient. This is called our coefficient, all right? I'm using the same letter a here as I did in the first number 1 up there, but in a different context. Another name that we give this little n up here is, other than the exponent, Glenn, is called the degree. The degree of the monomial, all right? And notice there that this number n, for the time being, is going to be over what set of numbers? We think of this degree number as being over the set of positive integers, which we have given another name called the set of natural numbers. Okay, this can be any natural number. And in fact, the number a here, this coefficient out front, can be what kind of number? In fact, it can be any real number. Most of the time, our examples that we select are always going to be usually integers, or perhaps occasionally we'll have a rational number in there, and what have you. Now, let's say a little bit more about the degree of these monomials, shall we? And suppose we were to have, well, let me take that example, 12x cubed. And we speak of the degree of this monomial as what, Donnie? 3. This is of degree 3, and of course if I were to write 12x squared, it would be of degree 2. Suppose I were to write 12x, it's of degree 1. Now, if I were to write simply the number 12, this is still a monomial. All right, it happens to be a constant monomial, the number 12, and it is of degree 0. Okay? Now, if I had the constant monomial of 0, what we do is to simply say that we do not have a degree number associated with 0. Okay? So let's just indicate that, in which we'll say here we have no degree number associated with this one. All right? Now notice here that our degree numbers are with respect to the variable. In this case, we have only one variable, 12x cubed. So we say that the degree of this monomial is 3. Is that right? Suppose we were to look at another example. Suppose I had something such as 12x cubed y squared. And here I have 2 variables, x and y. So if we speak of the degree with respect to x, or the degree in x, we simply think of it with respect to that exponent of x, which happens to be 3. So the degree in x is what number? 3. Is 3. And then the degree in y is what number? If we thought of this as the degree of this monomial with respect to y, it's of degree 2. If we then spoke simply of the degree of the monomial, all right, this is with respect to both x and y. So the degree of the monomial, we define it to be what? And does anyone remember that, Doug? The sum of the two. That's good. That's right. 2 plus 3, or indeed, we say that the degree of 12x cubed y squared is 5. All right? Well, let's see now what we can do. Looking at monomials, perhaps there's another characteristic that we can examine. suppose I happen to have, again, let me just pick an example, such as 12x cubed, and suppose we had negative 7x cubed, and 5x cubed. Notice that in each case we had the same variable x, and in fact they had the same degree in x, and when this is the case, we give these monomials a special name, and we call those what? Does anyone happen to remember what these are called? Doug?
Similar or like?
Similar, very good. Similar, or we should also speak of these as like monomials, all right? Similar or like monomials. So let's indicate right here, let me put in the word, these are like monomials. And suppose I were to have, 12x cubed, and say negative 7a cubed. Here they both happen to be of the third degree, but one is with respect to x, and this one with respect to a, so these are not like. And suppose we happen to have, such as 5x squared, and I think here we would call these unlike, L-I-K-E, or dissimilar monomials. Is that right? Now, from a monomial, what you can do is to take, say, two of these monomials, 12x cubed, and then, say, 5x squared, and add them together. You can combine other expressions from a monomial, and if we happen to have two of these, there's a special name that we have given that, and if you remember, we call those, Tim, well, it's a polynomial of two terms, and although the book doesn't use this word at this time, Tom, we have called them in this case, it's called a binomial. All right, a binomial. Suppose we happen to have a polynomial with three terms, 5x squared plus 3x. We may then refer to this as a what? Don? This was called, we call this a trinomial, three terms. All right. And usually after we have three terms, suppose we were to add another term here, say we have minus 7. All right, we generally refer to this simply as a polynomial of in this case, 4 terms. All right, and now notice each one of these is a term. It's considered to be a term. We are separating terms by a plus or a minus sign. So here we have our 4 terms in this polynomial. Is that right? So let me refer to these as polynomials. All right, and that's indeed exactly what we mean when we talk about the sums and differences of polynomials. We're talking about some expression similar to this. Well, let's see now. Let's take another example. Suppose we were to take one of these polynomials, such as 12x cubed plus 5x, and I happen to have a binomial here, and then let me take some other polynomial, 4x plus 3x cubed. And here we now have the sum of two binomials, all right? And what we would like to do is to simplify this if we possibly can, all right? We would like to simplify this polynomial. And the first thing that we have to ask ourselves is what is meant by a simplified polynomial. And notice here that we happen to have 12x cubed and 3x cubed, and what have we just called those two monomials? They are similar terms. And in fact, here we have a 5x and a 4x, and those two are considered similar. And so you say to yourself, well, I would like to write it so that we do not have any similar terms in our polynomial. And when that's the case, we'll have a simplified polynomial. All right? Let's go through as many steps here as is necessary in order to simplify an expression such as this. And let's see what we may say. Well, let's look at 12x cubed plus, and now let me rearrange our terms, 5x plus 4x, and then we have plus 3x cubed. And what is our reason for going from the first step to the second step here? All we've done was to regroup, and of course, also, that is our associative axiom with respect to addition. And let's look at that, and you say to yourself, well, I think I may use a property which enables me to rewrite this in this pattern, plus the 3x cubed. And what's the name of the axiom that we have used to go from one step to the next, Brenda? That is our distributive axiom. All right, let me just indicate it in this fashion. And now here we have 12x cubed plus 9x plus 3x cubed. And our reason for this is what? 5 plus 4 is 9. We have used the word, Tim, of substitution in order to be able to say that. And now right here we see that we may rewrite this as 12x cubed plus 3x cubed, all right, in fact, let me put some parentheses around that, plus 9x. And our reason to go from this step to this step is our commutative axiom with respect to addition. And you look at that and you say, well, I may rewrite this as 12 plus 3 times x cubed plus 9x. And our reason, again, is this is our distributive axiom. And now you look at that and we have 15x cubed plus 9x. And our reason for this is, again, Doug, our substitution axiom. And finally, you look at this expression and you ask yourself, are there any like terms in there? And you say, no. So what's your conclusion about our original expression in terms of our final result, and what then can we say? Huh? They are equivalent. Very good. All right, let me include right here a big gray symbol to indicate that our first line here is equivalent to the second expression, which is equivalent to the third, and so on all the way down finally to our final result here. Now let me write down that word, E-Q-U-I-V-A-L-E-N-T. These are equivalent expressions. And the reason they are equivalent, of course, is that whatever the value of the variable is that we will substitute, say in here, we then will get a number. Is that right? And now this equal symbol relates numbers. And if we then were to substitute the same number in here, sure enough we would have a number which would be equal to the number from this one, and similarly all the way up. And of course we then say that these are all equivalent. All right? Well, I don't expect you to have to go through every one of these steps every time you want to write one of these silly little expressions. Let's look at a few other examples. Suppose we were to take, well, let's just write some variations of the same one, plus 5x, and then suppose we were to have such as 4x minus 3x cubed. And looking at this, I would expect you to be able to look at that and in one step write down the final result and come up with its most simple name. So you look at it and you say, well, I see 12x cubed minus 3x cubed is 9x cubed plus 5x plus 4x is 9x, and you're done. Let's look then at, say, another example, 12x cubed plus 5x. So let's suppose we were to write minus. Now notice here, we can actually subtract these. Here we happen to have the difference of two binomials. And now let's see if we can't go to our final result here. 12x cubed minus a negative 3x cubed is 15x cubed. And 5x minus 4x is, of course, plus x. All right, and there we have the most simple name. And let's see what other variations we may write. Suppose we had 12x cubed minus 5x minus, and then here we have 4x minus 3x cubed, and I guess I can't get too many more dash symbols in there. And what may we say about this? 12x cubed minus the negative 3x cubed is 15x cubed, and minus 5x minus 4x is minus 9x, and we have our final result. All right? Well, let me give you your homework assignment for next time, and this will be assignment number 10.